Welcome to this video lesson. Here we will be looking at some practice questions on converting motion diagrams into position time graphs and some one-dimensional questions with displacement, position, and total distance. The first question is divided into 4 different sections, and the question in general is asking us that for the following ticker tape provided, given that the object is moving from C to A, so it's moving in this direction, sketch the position time graph and note that the reference point is stated on top of the graph. And the sign convention is also shown. So the sign convention for this first question is that east is in the positive direction. And we know that our reference point here is point B. So what I'm going to do for this is I will put my reference point here. And I know that I'm starting here and moving in this direction. So that's my final position. So I start here. So my first position is right here, my second one is right here, and then my third one is here, fourth, fifth, then my sixth one is right here. So we can see relative to position B, my first one is really far away and it's in the positive direction. So since my reference point is here, everything to the right is positive and everything to the left is negative for my positions. And right here at the reference point, that's this location over here. So my starting position, position 1, and at time 0, the object is all the way in this direction, and we got 1, 2, 3, 4, 5 points before we get to the center. So we start, I'm just gonna so for the very first position we're somewhere here, and then we get closer and closer to the center. So we get 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and the next one is right at the reference point. And after that, we can see that now my next position, because I'm moving still from 1 to 2, my next position is here, my next one is here, and then I keep going in that direction. So I'm not going to draw all of them, but you can see that they're getting bigger and bigger. And you can see that they're getting bigger and bigger now in the negative direction. So now I'm moving downwards. So this is going to be this way, and then this way, and then this way, and then this way, and more. And I have 1, 2, 3, 4, 5 points. So 1, 2, 3, 4, and 5 arrows in that direction. We can see that the spacing between the dots are all the same. So I'm going to draw a line kind of connecting all of this, and we get a nice straight line, kind of describing our motion. We can see it's straight, and since it's straight, we know that it's constant. As we discussed before, we can see that we're moving in the west direction, and we can see that the slope is also negative. So moving to the west, here we can see the slope or gradient is negative. And yeah, those are the information that we kind of know, and we know that the object starts from east position to our reference point, which is here, moves towards the reference point, and then moves further away from it in the opposite direction, or the negative direction. Let's try the next question. So we have the similar type of questions, another ticker tape, and again, same situation, we are starting from position C and moving towards A. So this is my reference point here. This is the very first point, so I'll draw a line to add very long distance to that one, and then the distance gets smaller. Now I'm all the way to the half position, and the distances are just the spacing between the dots are just getting smaller and smaller, and we can see that right here. So we can see that the spacing, I'm going to try to do this a little bit more precise. We can see we got from here 1, 2, 3, 4, 5, 6, 7, 8 points. And the last one is right at the reference point, so I'm going to place them here. So we got 1, 2, 3, 4, 5, 6, 7, and 8. And you can see that these are equal spacing because the time taken for each of these dots to be punched in are equal time intervals. So they could be every 1 second or 2 seconds. So either way, they're all the same spacing. Okay, so initially we can see that from our reference point, the starting position, because in the question we're told that it moves from C to A, the starting position is to the east and is very far away. So I'm going to draw that with a very, very large arrow, and that's going to be positive. I'm going to do it in gray. And you can see what I'm drawing here, kind of this arrow size here kind of matches this idea that this is the longest one. I'm just translating this into here. The next one gets shorter, and you can see the third one is actually, this position B is half of this. So I'm going to draw my second one actually right here. We already know that that's approximately half in terms of the scaling. The one before that was somewhere here, and the spacings after that just get shorter and shorter. So 1, 2, 3, 4, 5, 6 more. 1, 2, 3, 4, 5, 6. So there's another dip here, there's another dip here, another dip here, another dip here, another dip here, and the very last point is right at the reference point. So this last point, this one, is just right at the reference point. And if I were to connect all of these points, we get a nice curve going in this direction. And this one is curved, so we know it's no longer at a constant velocity or constant speed. And we know that in terms of speed, it's kind of like going fast. There's a lot of displacement from the first to the second point, and then that displacement gets less. Then the displacement gets less and less between each point. So that means the object is slowing down. And so I'm going to write that down so we know that it's slowing down. And we also know that it's starting from east of our reference point, because this direction is east, this direction is west. In this one, east is this way, west is this way. Again, in this one, because of this convention which says position is in the east direction or positive in the east, this direction is east and this direction is west. And we know that it's starting from a position in the east and it's moving towards the reference, and that means it's moving in the west direction. So moving west. Let's look at the next graph. Okay, we get this one over here, and it's a similar situation actually as the one before, except our reference point has now changed position to here. And we're starting at this point over here, and our second point is here, our third one is here, and then fourth one, fifth. You can see my arrows are just becoming more and less straight. But we're gonna keep moving until we reach the very, very last point. Now let's put this into our graph. We can see that the very, very first point is here, so that's going to be, and there's no arrows to that, it's just right on the reference point. The next point, the distance, so we have about 9 total. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And my second one, in terms of spacing, it's actually, let's do some that we know for sure. So we know that this is kind of halfway. So the second point is kind of halfway. So I'll draw that, and it's in the negative direction because everything to the right of my reference point here, based on my sign convention, is positive, and everything to the left here is negative. So this one is kind of halfway, and my very last point is the furthest away, and the furthest away approximately twice as lengthy as the other one, and that one is also the negative. So I just plotted this one. So I plotted this and I plotted this one, and now I'm going to try plotting this one. So for this one, kind of a little bit more than halfway, that's going to be here. The next one is going to be still, it's growing in distance, so I'm going to draw that about here. And then we get the next one, still increasing in distance, and then next one. And you can see that the distance between them is starting to get shorter and shorter. So that's this one. The next one is somewhere here. So you can see that the difference between these two is very little. The difference between these two is a little bit more. The difference between these ones is more, and the difference between this one is very large, and the difference between the next one is still large but smaller than the last one. So anyways, once you have all of those, you're going to connect them, and with a nice smooth curve, and you get this beautiful curve right here. And we can see that in terms of direction, it's moving, starting at the reference point, it's moving in the west direction. So moving west. And in terms of whether it's speeding or slowing down, you can see that initially it's traveled a lot, and then it didn't travel as much in the next section. It didn't travel as much in the next section, and this got smaller and smaller. So this is definitely slowing down. Let's look at the next question. So this one is quite a bit more stuff going on in this one. We're still moving from 1 to 2. This one I'm going to break it down into intervals. So we have, actually I'm going to break this down to 2 here, 3 here, change this last one to 4. And the reason why I'm doing that is because you can see that the object is kind of speeding up from this section to this section. It has quite a bit of constant speed here, and then it slows down at the end. There's quite a bit of a number of points here. We start 1, and then 2, 3, 4, 5, 6, 7, 8. So instead of doing 16 points, I'm just going to do the 8 so that it's a little bit easier. So 1, 2, 3, 4, 5, 6, 7, and 8. And let's see how these are. So we start at our reference point, which is here. Usually if you have a question like this, make sure you do every point. For now, just to make this a little bit simpler, I'm just going to do these points. I'm going to draw the middle points here as well, just for sake of completion. And this is going to be the first one, then the next one, next one, so that's this one. So now I'm doing all the middle points. This one, oh whoops, that's right here. This one, this one, And then we get the last one, which is approximately here. Now, all I'm translating, I'm pretty much translating all of these points into my graph. So we start from 0 points here. So the very first point is right here. And then we start moving just a tiny bit. And then we move a little bit more. And then we're starting to move more and more as we go. Oh, whoops. So this one is going to be even more, and then next one is going to be even more. So I've done up to this point, and from here on, we can see that everything else is kind of at a constant speed, so that the change in spacing between them doesn't really change. So I'm going to try to do that pretty nicely here. 1, 2, 3. I think this one should be a little bit longer. And my next one, I'm plotting this one right now, kind of here. And then from this point on, you can see that spacing gets smaller and smaller as you go. So the spacing is getting smaller and smaller, and I'm going to represent that here. So spacing, it's not as long anymore. It gets shorter and shorter as we move towards the end. And then we plot this. We see that initially it kind of starts to speed up, and then for a while it goes at a constant speed, and then it starts to slow down. And you can see that curve. You can see that this is kind of like stage 1, and stage 2 is right here from this point to this point here, moving at a constant velocity or speed, and then it starts to slow down until the very end. So we get the first section where the spacing starts to increase, and then it goes at a constant one, and then it slows down. So we can break this down into intervals, so this is event 1 to 2, 2 to 3, and 3 to 4. And between 1 to 2, it speeds up, and then it's constant, and then it slows down. And in terms of direction, it's always, here's a reference, it's always moving in the west of our reference point. So we are always going to, in each point, write that it's moving west. And that's how we transfer our diagrams, our motion diagrams, into position time graph. We always show where the reference is, and we plot our positions from the reference point to the position. We draw a vector, and then we translate those vectors into our position time graph, and our position time graph always has the reference point right at the x-axis or the time axis. All right, the next question we have is when Roxana is walking her cat. Starting from home, she walks 80 meters east to Park A. So I'm just going to highlight whenever you have a question which just has a lot of parts to it, just try highlighting all the important information. So 80 meters east to Park A. There's a dog at the park, and she turns around and walks 120 meters east to Park B. Then she decides to stop at the pet shop for a cat treat, which is 35 meters west, and that's the pet shop. Label the locations of Park A, B, and the pet shop on the diagram below. Okay, in this question, we got 2 units is 10 meters. So starting from home, which is here, Roxana travels 80 meters east. So if each 2 units is 10, so that's 10, 20, 30, 40, 50, 60, 70, and 80. So right here, I'm going to put my first dot or point, and this is going to be Park A. Now I have Park A. She then turns around and walks 120 meters west, so I forgot to put my positive east direction. So that's my sign convention, that's positive east. So whenever Roxana is traveling east, that's to the right, and whenever she is traveling to west, that would be opposite to east or to west. So from here, 120 meters west. From here to here is 80 meters, so that's 80, 90, 100, 110, and 120. So right there, this is going to be Park B. She then walks another 35 meters west. So from starting here, that's 10, 20, 30, and 35. So it's right there. And this is the pet shop. And in terms of where she starts here. So I will label that 1, goes to here, 2, and then 3, and then 4. Now I've done the first part of the question. The second part is asking us to use vectors to sketch the path that Roxana and her cat walked. So let's do that here. Starting from here, they go in this direction all the way to here. They then travel in this direction and they go right here. And then from here, they move to right here, 35 meters. So that's right here. All right, now using home as a reference, state her positions at each location. Okay, in this case, we're taking home to be referenced. That's right here. I'm going to draw a nice line up in this direction, and anything to the right would be positive, and anything to the left of this would be negative in terms of my position. So let's do all the positions. Position for home. So I will also label 1 is home, 2 is Park A, 3 is Park B, and 4 is the pet shop. So the first position here that I am going to write is home. And from this reference point, the home is right at the reference point. So there's no movement involved at all. So this is 0. In terms of units, we are dealing with meters. And I've taken my right or east direction to be positive. So I'm just going to label that. In this case, 0 meters east or west is the same thing. It doesn't really matter, but I will label it. And I need to label my questions as well. So this is question 1, this is question 2, this is question 3. So then I will do my position 2. My position 2 from the reference point, here's my reference point. Position 2 is, I can just count these, but I already know that it's 80 meters east. So from here to here, position 2 is 80 meters, and it is in the east direction. How about position 3? Well, let's do that. Position 3 is the park. That's Park B. And from this reference point, I can just count. This is 10, 20, 30, 40 meters. So the magnitude is 40. Unit is meters. And this time, I'm in the left-hand side. So I can either write this as 40 meters west, or I can write it as negative 40 meters in the east direction, and both answers are acceptable. How about position 4? Well, let's see. Position 4 with reference to this point. Up to here, I had gone 40, and then I'm going 50, 60, 70, and 75 meters. So that's 75 meters west or negative 75 meters east. Again, both answers are acceptable. This can also be written as negative 80 meters west if you wanted to. So we can see that when we want to find the position, we always look at the reference point and we see how far those locations are from, or how far those positions are from our reference point. Question 4 asks us to calculate the displacement from from home to park A. Okay, let's do question 4 here. So the first thing we want to do is to find the displacement. For displacement, that's change in position. And we want it from, the first one is from home to park A. So home is 1 and park A is 2. To do this, I will subtract position 2 from position 1. And taking right to be positive, I will have position 2, which is 80 meters east. So since it's east and positive, I'm going to leave it positive. Position 1 is 0, so it will end up being 80 meters east. In this question, it says calculate the displacement. So the keyword calculate means I have to show some work. So you can show this in different ways, but this would be one way of showing it. So that's displacement 1 to 2. That's my first answer. I will box my answer here, or you can highlight it. And then we're also asked to find a displacement from park A to park B. So park A is number 2, park B is number 3. So that's going to be position 3 minus position 2. Again, I'm going to take east to be positive, and position 3 is negative 40 meters east, so I'm going to write negative 40, and position 2 is 80 meters east, so that's going to be minus 80. And east is positive, so I'm going to subtract it by a positive value. This is going to be negative 120 meters in the east direction. I will box this answer as well. And then for the next one, I have my displacement. So I'm just going to scroll a little bit so we have a little bit more spacing. And we have displacement from park B to the pet shop. So that's park B for my number is number 3. And I'm going to the pet shop, which is 4. So that's taking position 4 and subtracting it by position 3. Position 4, we can see that it's negative 75 meters east. And since I'm taking east to be positive, I'm going to put negative 75 here. And position 3 is, so I'm subtracting, and position 3 is negative 40 in the east direction. So then negative 75 minus negative, make it positive, and this will become negative 35 meters. And since my positive direction is in the east direction, I have to label this as east. And I will box this answer. Now, question 5 tells us hence or otherwise. So the keyword hence means to use the information from previous parts. It could be any of these parts. Or otherwise says you can use another method if you want. Algebraically, so we have to use algebraic methods, calculate the total displacement. Okay, so for the total displacement, it can be done in 2 ways. Maybe I'll do both. So one way is the total displacement is from the beginning to the end. So that's from the home all the way to the pet shop. and that's going to be one way of doing it is from the final position minus the initial one. So again, that's 4 minus 1. And I'm going to take east to be positive here. And in this case, position 4 here is negative 75 meters in the east direction. And I'm going to subtract that by position 1, which is just 0. And that's going to give me 75 meters east. And there's another way of doing this, and in that one, the total displacement again is the same. Total displacements from 1 to 4. I'm miswriting the total displacement in the last one, but that's okay. And we can add all the displacements. That's from 1 to 2 plus displacement 2 to 3 plus displacement 3 to 4. I have my east direction to be positive. And I have all my values here. So this is positive 80 meters in the east direction. This is negative 120 meters in the east direction. And this is negative 35 meters in the east direction. So I will have, I'm actually going to write the equal here, 80 plus negative 120 plus negative 35. And that will end up getting me a value of negative 75 meters. And my direction, I took right to be positive, so I'm going to use that here. So my final value is negative 75 meters to the east or 75 meters to the west. And both methods work, so you choose whichever method you feel more comfortable with. If we had already calculated this information and didn't have to calculate this information, then this would be the most efficient method. But if you had calculated this method, or if you had this information and not this information, this would be the most efficient method. Part 6 is asking us, so that was part 5. I don't know why I labeled it as part 4. So I'm going to put 5 there. And I'm going to go up a little bit. Question 6 says, algebraically calculate the total distance traveled. So, and question 7 says, use a vector diagram to show that her total displacement agrees with your calculation. So we can do both of them here. So for question number 6, we know that the total distance traveled from 1 to 4, no longer vector, so I don't put the arrow sign here. That's going to equal to the distance from 1 to 2 plus the distance from 2 to 3 plus the distance from 3 to 4. The distance from 1 to 2, that's 80. Distance 2 to 3 is 120. Again, I don't care about the negative sign when I'm dealing with distances. And distance 3 to 4 is 35. So I'm going to put all of those values in. I am going to have 80 plus 120 plus 35. Putting everything together, I will get a value of 235 meters. I don't need a direction, and therefore I am not going to include one in this case. And I'm going to put an or here because both methods work. And finally, the last question, it says to check to see if your displacement is correct using the vector diagram. And my vector diagram is already here, so I'm just going to use the same one in this question. Or actually, let's do the new one. It doesn't really matter. We can just do a new one. 7. We start here, we move in this direction for 80 meters. And then we move back. I'm going to use the green again in this direction. And we go for 120 meters. And then we go from here to here for another 35 meters. And our total displacement when we add vectors starts from I'll do it in purple actually. It will start from the very beginning. So this is the initial point, and it goes to the head. So tail of the initial vector to the head of the very final vector. So that's this distance over here. So we can calculate that based on our vectors actually. Algebraically, it's just adding the vectors like this, but vector-wise, 80 meters travel 120 this way, so this little section here is 40 meters west. Add another 35 meters in the west direction, and I will end up getting 75 meters west. And we can see that these are consistent, and therefore both vector and algebraic method results in total displacement of 75 meters west. And really in this question, the main part is the method marks here, and sometimes you need a concluding statement, and sometimes you just need to show your work. And I hope that this video helps you a little bit with these types of questions. Again, if you're having trouble with it, try the question again and see how it goes, and then come back and kind of check your solution.